Good morning, ladies and gentlemen. May I have your attention, please? Thank you. As you know, we'll be taking our Unit 6 quiz. We're going to be taking that second half, and so let's get started right away to make sure you have plenty of time to do your very best. Today's Bellwork was 2 parts. The first part, I want you to use graphs and tables on your graphing calculator in order to answer these 3 questions. And so let's suppose that we have the path of a projectile object, and it's given by the height h above ground after t seconds is negative 16t squared plus 48t plus 0. Let's go ahead and use our graphing calculator to answer questions like, what's the height after 1 second? What's the highest point for the object? And when will the object hit the ground? So the first thing I want to do is just using the graphing calculator technology, and this will help remind you for the second part of your quiz how you can answer some questions using your grapher. The next part then we'll do without the graphing calculator, right? Without the graphing calculator, we'll consider how we can do that algebraically. Some of these we will be able to do, some of these we won't. Let's go ahead and get started then with our grapher. So I'm going to go ahead with my graphing calculator, enter my original function. So I'll go ahead and make sure my y equals menu is cleared out. I'm going to zoom 6 to return to my standard viewing window and then adjust it later. And I also want to make sure that my plots are off. So once again, if they're darkened, you want to highlight, you want to up arrow and press enter to turn them off. So all of your plots should be unhighlighted so they're off, and that won't interfere with our window. All right, let's go ahead and consider my original equation, negative 16t squared plus 48t plus 0, and I don't have to enter that plus 0, right? I don't have to enter that plus 0 because it looks like that's not going to have any effect on my graph. All right, so what is the height after 1 second? Well, after entering this in my calculator, I could go ahead and go to the table, right? Remember, I go to the table by doing second graph, and that'll pull up the table, and I can scroll along that and find the height that corresponds to a time value of 1 second. So it looks to me like if I were to go ahead and scroll along my table, it appears that the height is, what is that, 32? Did you guys get 32? Awesome. So it looks like the table is telling me 32. The second way I could do it is to use the graph and do that trace. I could do trace and then tell the calculator I wanted to know what the value of the function is when x equals 1 second. And so then I'd go trace 1, enter. To do that, let's go ahead and get an appropriate window. So I'm going to change my window. I want to see what this looks like. So I'm going to go maybe -1 to 4. And I'm going to go negative 20 to 60. Now, I might not like this window at all, right? But I won't know until I try. If I don't like it, then I'll simply go back and I'll change my window manually again, like we did last class. So I'll go ahead and take a look at the picture. And by golly, it appears as though this is a decent window because I can see the behavior of that object. I would expect it to be going up, 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 reaches the maximum height, then coming back down, and then hitting the ground. So it looks to me like that's a fine window. So I'm going to save that. So I could do trace, x value of concern, that's 1, enter, and the calculator will put the cursor on the graph at the point when x equals 1 and pair it with that corresponding output. In this case, my height is the y-coordinate 32, and so that'll be 32, and I've gotten a couple different ways. All right, so I'm going to go ahead and state my answer then, and make sure you include units on your quiz as well. So I'm getting 32, but I'm getting 32 feet, right, as the label on there. And how do I know that this is feet and not meters or yards? What was it about my original equation that let me know that this is going to be feet for my label on height? Joe?
What was the question?
Oh, what gives it away that this is going to be feet for my label based on the original?
16.
Absolutely, thank you, the negative 16. So the negative 16 as the coefficient on my quadratic term, the t squared, is telling me automatically I'm working with the distance measurement of feet as my unit. Good job. Okay, raise your hand if you got 32 feet. Sorry, raise your hand if you got 32 feet already. Easy cheesy, good job. What about the highest point on the graph? How could I find that using the built-in capabilities of my grapher? We'll have to do that on your quiz, so I can do second trace of the calculate menu. Everybody, let's remind ourselves how to do that. So second trace is the calculate menu, and I want the fourth option, maximum. So I'm going to go ahead and find maximum, the fourth option. And I'll select that, and then I'll use the cursor to go to the left side of where I think that occurs. It looks like I'm already there. Press enter. And then I'll use the cursor to go to the right of where I think that maximum occurs. So I'll have to move the cursor this time. I'm going to make sure I go a little bit past. So I'll go to the right of where I think the feature occurs, enter. And then now I'll toggle back for a guess before pressing the cursor a third and final time. Voila! It appears as though the maximum occurs when x equals 1.499999996. What do you think that's trying to tell me? Right. Do you think it's really 1.499999996 exactly? No, the calculator's probably trying to tell me. Remember, it's just making an approximation. It's probably trying to tell me 1.5. Right? It's probably trying to tell me 1.5. And so it appears as though a maximum occurs at x equals 1.5 seconds, and the height is 36. So what's the highest point? Looks like the highest point is 36 feet above ground. Sweet house. Raise your hand if you successfully calculated the maximum using your grapher. So who else had 36 feet using your grapher? Hey, that's great. You're going to have to do that in your quiz. Right? You have to do that same thing in your quiz. Some point. And lastly, when will the object hit the ground? Graphically, right? When does the object hit the ground? Graphically, that's right there. So I want to see when, right? I want to see when that parabola comes back down and touches the x-axis. So I can calculate that as well. I'll do the second trace as the calculate menu, but this time I won't select maximum, I'll select 0. That's where the 0 of the function is an x-intercept of the graph. So again, second trace is the calculate menu, but this time I want 0. First curve, nope, left bound, I want to be to the left of where I think that feature occurs. And I'm already on the left-hand side, but I'm going to get just a little bit closer. Just a little bit closer before telling the calculator, yep. The right bound means tell the calculator the right side of the window in which you want it to look for the given feature. So I'm going to go to the right of this x-intercept over there. Gosh. You've really got a lot of screenshots, Mr. Fritz. I do have a lot of screenshots. And then, yes, so I'll toggle back a little bit closer. And then, voila! The calculator puts the cursor right on the x-intercept. It looks like the x-coordinate 3 is paired with the y-coordinate 0. So it looks to me like, yes, we found the 0. The object will hit the ground at x equals 3 seconds. Awesome. Raise your hand if you already had 3 seconds. 3 seconds, you're going to have to do that in a quiz. Way to go. You guys have 3 quiz questions already taken care of. Way to go. That's awesome. What questions do you guys have on the calculator applications? Now let's take a step back and let's consider, what if we had done this non-calculator? Can we answer these questions without a calculator? That is, what's the height after 1 second? Well, do I have a function rule that gives me the height h after any time t? Yeah, we could simply evaluate that without the graph by doing h of t equals, and I'll rewrite my original rule, negative 16 t squared plus 48 times t. It's just that I won't use t, I'll use 1 for 1 second. And you got it. And so we could certainly do this without a graph or without the graphing calculator. And I get negative 16 plus 48. I'm getting 32. Hey, that's familiar, isn't it? Bam! 32 feet. That's my height after 1 second. So 32 feet. Awesome. What about the highest point? What about the highest point for the object? Well, if we've successfully made a graph, right, the highest point for the object, then we could determine it if we could figure out the coordinates of that vertex. And so without the graph, right, without the graph, that's going to be a little bit trickier. And as a matter of fact, right, we'd have to be able to find the y-coordinate of the vertex, and we haven't done that yet. So this one we could reason out number 2 after we do number 3, but for now we'll say that would be the y-coordinate of the vertex. We have to find the y-coordinate of the vertex, and we will be able to do that in another 2 days. So the y-coordinate of the vertex. We will be able to do that. Another couple of days. For now, we'll hold that off. And I'm going to scooch that up a little bit. When will the object hit the ground? We need to be able to do that. Well, algebraically, when does the object hit the ground? Well, what's true about the value of h when the object hits the ground? What must the value of h be when the object hits the ground? Ian?
0.
0, absolutely. So if I rewrite my original equation, except put a 0 right there for h and solve for t, that would tell me the times t when the object is at ground level. So let's go ahead and set h equal to 0 and then solve. Negative 16t squared plus 48t. Can we solve this equation? Well, certainly. It's already set equal to 0. And so I could try factoring this. It turns out that this is an easy factor problem because there's no constant term here. In fact, I can do this just with a GCF problem. Stop. Think. GCF. Is there a greatest common factor hiding inside each of those terms that I could pull out in a reverse distributive property problem? And the answer is, you bet your boots. We could pull out a negative 16 and a t. So I'm going to go ahead and pull out negative 16 and a t and rewrite in a reverse distributive property problem. Inside I have t minus 3. If I multiply that negative 16t through the parentheses, I would get my original polynomial. I'd get negative 16t squared plus 48. Therefore, I know I factored correctly. After I factored completely, I can set each individual factor equal to 0 and solve separately. So for this one, I could set negative 16t equal to 0, or I could set t minus 3 equal to 0. In each case, the solutions of each of those factors, right, set equal to 0, are going to be the values of t when the entire thing equals 0 in accordance with the zero product property. So dividing both sides by negative 16, I get t equals 0. So the object is at ground level at time t equals 0. Well, that makes sense because that's where we started. So this object started at ground level, all right? And then what about the other one? I'd add over 3, and I get t equals 3 seconds. So we got that graphically when we did second calculate 0, but we also were able to do it algebraically. So how do I find how long an object was in the air using projectile motion? I set h equal to 0 and solve for t. Depending upon what the equation looks like, you might use a different method, and yet our concept, our strategy was the same. We still set h equals 0 and solve for t. What questions do you guys have about our Bellwork today? All right, now that I know my times t when the object is at ground level, that is 0 and 3, could we reason out the highest point for the object? Well, we could certainly reason out the time it takes to get to the highest point using the symmetry of the graph. I know that a parabola, right, has an axis of symmetry, a line of symmetry that divides the parabola into two equal halves, two left-right halves. There's reflectional symmetry. So if I knew the answer to number 3, I could reason out the answer to number 2 using my knowledge of a parabola. If this happens, if I get to ground level at t equals 0 and t equals 3, could I reason out the time it takes to get to the maximum height? Yeah, using the symmetry of the graph, what would the time be it takes to get to maximum height? 1.5, right? Halfway between 0 and 3 is 1.5. If I knew the time it took to get to maximum height, could I then determine the maximum height? Yes. What would I do? I'd plug 1.5 in for t, just like we did in number 1, and evaluate. And so I could find h of 1.5, and that would be the height of the object, the maximum height of the object reached. So I kind of went backwards here. If we knew the answer to number 3, then we could go backwards. Now that's not always going to be the case in terms of taking half of this, because oftentimes we start above ground, like at h equals 7 or h equals 2. Remember in our examples last class, we started with the ball already here, and so we can't just take half the time it takes to hit the ground. We can't just always do that because we're not always starting at ground level. Is that what you're going to ask, John? Yeah. So this was special because we start at at height equals 0, at time t equals 0. So that was special about this one. We can't always just take half of the time it takes to hit the ground. That's not always going to work. But here we kind of use that to our advantage. All right, we will find how to do that and find the y-coordinate of the vertex in the upcoming days. But now let's go ahead and take care of our discussion for the first half. We've talked several times about this now. You want to make sure if you're interested in applying for the compacted course that you must sign up in the FlexiSked offerings for one day next Tuesday through Friday. You have to sign up and attend one of the informational meetings if you'd like to apply for the compacted course. We'll share important information as well as application materials and deadlines. So if you want to apply for a compacted course, you have to attend one of these sessions. Remember, there's a lot of options here, so if you have individual questions about what you should do or what you think you should do, then please see me outside of regular class, and I'd be happy to steer you in the right direction as best I see fit, or direct you to talk to your first semester advanced algebra teacher if they know you better than I do, and you can go ahead and come up with a plan. The registration meetings are off and running, and some of you have already met. All right, let's go ahead and take care of homework from last time. And I know we're a little out of order. That's okay. I would ask that everybody take out your homework assignment and make sure that you have your name, 2A, and number 4 clearly labeled before giving yourself an infinite campus score. I'm going to pause the recording during the homework check, and I'll resume it when we resume our discussion. Okay, ladies and gentlemen, so let's review when is the most efficient to solve a quadratic equation using a particular method. And so far we've got 3 different methods we can use to solve a quadratic equation. We can solve by taking square roots, we can solve by factoring, and we can solve by completing the square. It's most efficient to solve by taking square roots, but I can only do that if I have a single squaring term. So if I have a single variable term squared, either an x squared or a quantity squared, right, then I can solve by taking square roots. And so if I have a single squaring term, then it's appropriate to solve by taking square roots. So that in this standard form, that would have been when b equals 0, and there's just an x squared term or a parentheses squared term, but no other x term. If I have an x squared and an x term mixed together, that is quadratic and a linear term in the same problem, so I've got an x squared and an x somewhere, then I can't solve by taking square roots directly. So I'll have to go ahead and rewrite in standard form everything on one side set equal to 0 and try to factor. That would be the most efficient way if there's x squareds and x's mixed together. So I'm going to say both quadratic and linear terms present. So recall that quadratic is my x squared type term, and linear is my x type term. Then I'll try to factor. If I've gotten in standard form set equal to 0, right, and tried to factor, but I can't factor, then I'll go ahead and use our third method. That is completing the square. So that's what I'll do, completing the square. So I'm going to go ahead and, of course, grab this and clone it. And you're going to be like, I wish I had a smart board. I'm going to be like, yeah, I lobbied the school board to have one, right, installed in our family room in the basement so that I could practice my lessons with the smart board and cloning and grouping, right, just to, better myself and have more strategies to share with. But I was denied. In any case, I'm now going to utilize the clone grouping feature right now to get this down here, but I can't factor. Then I'll use completing square. And this is I can't factor because it's either unfactorable, or I don't recognize the factors, or I'm not good at factoring. Right, then I'll go ahead and use complete the square as a means for rewriting, right, so that I have a single squaring term, and then I can solve by taking square roots. What questions do you have about our 3 different methods? So you will have to solve algebraically for quadratic equations. A couple of questions on the first part of the quiz, non-calculator, using these methods based on what it looks like. Awesome. Let's go ahead and address our objectives today, and then we'll get going on your quiz. And so please listen carefully. Today we're going to fit a parabola to given data points. And so we're going to be using the built-in capabilities of your graphers to find a parabola of best fit. Think back to first semester. We had to find a line of best fit, right? We had to find a line of best fit using the technique called linear regression. Today, when we use quadratic regression, we're just finding a parabola that does a good job of, or the best job possible, of going through a scatter plots of individual data points. And so, we're going to take our quiz second half after we perform quadratic regression with the graphers. So, recall, how many points on a line do we need to be able to write its equation? Well, if we're talking about writing a unique equation for a line, we would need at least one. Well, we'd have to know 2 points. But if we know 2 points that are on that line, then there's only one way that we can connect those 2 points together and get a line. So how many points do we need if we're going to write the equation of a line that is a first degree polynomial? We need 2 points. All right, we need 2 points in order to write the equation of a line. 2 points uniquely determine a line. So then what if we were trying to write the equation of a parabola that is a y equals x squared, a degree polynomial? Then how many points would we need? Well, would 2 points be sufficient? Right? Would the same 2 points be sufficient for determining a parabola if a parabola contained these? Well, visually, you guys can probably see that that's probably not enough, because I could draw a parabola like that goes through those 2 points, but Joe could come up here and draw a parabola like this that goes through those 2 points, right? And then Hannah could come and she could draw a parabola that's like this. It still goes through those 2 points. You see what I'm saying? And so is 2 points, are 2 points sufficient for determining a unique parabola? No. If I needed 2 points to determine a unique degree 1 polynomial, that is a line, how many points do you think I need to determine a unique parabola degree 2? How many points do I need to determine a unique parabola? 3. I need 1 more. So if there were 2 points needed to draw a line, all right, that's literally a polynomial x to the first degree. I need 3 points in order to determine. Once I put in a 3rd point, then there's only 1 parabola that will connect all those 3 points exactly. Okay, so I need 3 points. Now, if we're given real life data, then none of the points may fall exactly on the parabola. It's the shape of it, rather, that's going to determine that we use quadratic regression. And so we're going to do both. Let's go ahead and consider a parabola that contains the points -1, 8, 1, 2, and 3, 4. We'll find its equation. One way to find the parabola's equation is by using the quadratic regression command in your graphing calculator. So once again, we're going to use the graphers, and this is a great review for the regression process. Everybody, we can enter the x coordinates into the stat menu in list 1. So we're going to go ahead and put the x's in list 1. So my x coordinates of the points, I'm going to input into list 1. For the y coordinates, the corresponding y coordinates of each point, I'm going to input into list 2, just like we did in first semester, right, with linear regression or exponential regression. So everybody, let's go ahead and practice together. Everybody do stat, edit, and we're going to enter our x coordinates of each point in list 1. Now when you go there, you might have data already in your lists. That's fine. You can just up arrow and highlight the list title and then press clear before down arrowing, and it'll automatically clear out your list. So everybody find list 1. Everybody find list 1. Go ahead and enter your x values in list 1 for my points. So I'm only putting my x values. That's -1, 1, and 3. Those are the x coordinates of each of the points in order. I'll enter the corresponding y values, right, in list 2. Make sure that they match. So I have -1 is paired with 8, enter. 1 is paired with 2, enter. And 3 is paired with 4. So at this time, make sure that you have them entered correctly in your graphing calculator. Once again, that's stat, edit, x is in list 1, y is in list 2. Now we'll go ahead and perform the quadratic regression. You guessed it, and we go to our stat menu again. But this time we don't edit, we go to calc. So everybody go stat, and then right arrow to the calculate menu, stat calc. And now we want which option? Looks like the 5th option. The 5th option is quadratic regression. Listen carefully, because I'm going to share with you how you can put this in your y equals menu. So I'm going to share with you how you can put this in your y equals menu. So we've got our quadratic regression. We're going to do enter. And for the first one, I think we're going to make a scatter plot, so I'm not going to store it this time. I'm just going to make sure that list 1 is paired with list 2. The x's were in list 1. We edited list 1 for x's. The y's we put in list 2, so that's good. I'm going to go right down to calculate. I'm not going to store the equation this time because I think we're going to make a scatter plot. I want to see how we do. So it looks to me like the calculator determines the values for a, b, and c in standard form. So it looks like my quadratic equation, y equals ax squared plus bx plus c, must be given by y equals 1x squared minus 3x plus 4. So I'm getting 1x squared minus 3x plus 4. Everybody take a minute and do stat, calc, quadratic, enter, and raise your hand when you produce this equation, this screen on your calculator. So raise your hand when you've got it. Where you got it? You have to be able to do quadratic regression on your own. Way to go. That's great. Now let's go ahead and consider the points in a scatter plot and compare my equation with that scatter plot. So everybody, we're going to graph a scatter plot of those points and the parabola from the regression equation on the same window. First, we're going to do the scatter plot only. So we're doing points only. No y equals menu. Instead, we're going to do a scatter plot. How do we do that? Easy cheesy. We'll go ahead and we'll go to our y equals, but we'll go second y equals, and we're going to turn our, well, we can go y equals, and we're going to turn our plot 1 on. So clear out all the other business. We're going to clear out your y equals menu, and you're going to up arrow and press enter to turn plot 1 on. So go ahead and up arrow to turn plot 1 on, enter. And then down arrow, everybody should have a highlighted plot 1 now. Plot 1 should be highlighted. Is everybody good? Highlight plot 1? Great. Now let's go ahead and zoom 6 to return to a standard viewing window and check out our picture. I see, well, 3 points plotted. Right? That's not much. That's not much of a scatter plot. You guys see 3 points? Everybody good? Now let's go ahead and see how our equation does, right? How good of a job our equation does with connecting those points, right? Or modeling the trend through those points. So here we go. Ready? Go to your y equals menu and let's enter our equation. Oh, I want that picture. Sorry. Just for the notes, I want to save that picture. All right, ready? In our y equals menu, let's go ahead and enter our predicted parabola. 1x squared minus 3x plus 4. We got it? So I'm going to go ahead now and put this on the same window and see how good of a job it does. My. That looks pretty good. So I've got my scatter plot and my predicted equation on the same window, and it looks like it does a good job. My parabola does a great job, as a matter of fact, of going through those points. So how well does the curve fit the points? I would say very well. Is real world data this clean, this nice to work with? No. Oftentimes we look for trends in a scatter plot, right? And see if a quadratic equation would best model that, and we can do that kind of by the shape, right? By the shape. But we're not going to be able to write a parabola that goes through all the points in a scatter plot. Usually, this one was made up to practice the process. So let's go ahead and look at some real world data. Let's consider the following data, which gives the number n of patient applications in thousands as a function of the number of years t since 1990. Let's go ahead and use quadratic regression to find a best fitting parabola to model that data. So again, in our grapher, we're going to clear out our stat list 1 and list 2. So we'll go stat, everybody go stat, edit, and we're going to up arrow to clear out the data in my list 1 and list 2. So up arrow to highlight the list title, press clear, and then down, and that'll clear out the data. Go and up arrow to highlight the list title, list 1, and press clear, and then down arrow, and it should clear out the data. Is everybody able to clear your list? Alternatively, you could overwrite it, right? Because we have more data here, you could just overwrite it, and that would be fine as well. But if we're going to go to fewer entries, then we'd have to clear out the lists. So here we go. Everybody do it. 0, 5, 10, etc. Oh, 16. Doesn't go by 5s the whole way. 0, 5, 10, 15, 16, 17, 18, 19. Take a minute to make sure that you have your data entered correctly. Right, so take a minute and make sure you have the correct data. 213, Otherwise, it's going to mess everything up. Now let's look at a scatter plot and see how real world data is and as clean as those nice 3 points that we picked. So we're going to do a scatter plot first. I already have my plot 1 on, but I need to change the window to make sure I get an appropriate viewing window so I can see these points. Is negative 10 to 10 going to be sufficient? No. We have my time values going from 0 to 19, so I need my x window to go to the left of 0 and to the right of 19. So I'm going to go ahead and choose negative 5 to 25. I'm going to go a little bit past for my x window. Everybody do it. Window. Sorry. Oh, I gotta take a picture of this. Sorry. Everybody do it. Window. Negative 5 to 25. And I'm going to go less than and greater than. So I'm going to go ahead and go maybe 100 to 500 so that I'm below my lowest value and I'm above my highest value and give a little space. So I'm going to try 100 as my low Y min, and I'm going to try 500 as my largest Y max. Let's go ahead and see what that looks like. This may or may not be good. Hey, not too shabby. What's that? Did I not clear out my Y equals? That might be our old one. Sorry, I didn't clear out my old one. So I want to clear out my old one. That has nothing to do with this one. All right, how do we do? Well, this looks like a scatter plot. This is more like real world data. All right, now let's go ahead and get the regression equation. Where do we go to do that? We did stat, calculate, and I want the fifth option for quadratic regression. Guys, I'm now going to tell you how to store it in your Y equals menu so you don't have to copy down all the decimal places. And so this is super powerful skill. If we now store this, in our Y equals menu, if you have an 83, right, you'll still do the same exact commands. So you're going to go ahead and do bars. You're going to do bars. Everybody look. Bars. Y bars. Function. Y1. It's just the first option. Enter. And it's going to automatically store that regression equation in the Y equals menu when it calculates it. And so I've calculated it just like before on our home screen, but look at all those decimals. If we don't want to run the risk of copying down those decimals incorrectly or punching them into our calculator in the Y equals menu incorrectly, we can store that in our Y equals menu by pressing bars, Y bars, function, Y1, enter, and watch. When I go to my Y equals menu, it's already in there. So it's already entered it in there and kept all the decimal places. How sweet is that? I don't have to worry about compromising accuracy or a copy error or a typing error. Let's go ahead and see how well the parabola does. Very nice. It appears as though that best fitting parabola is not going to hit all the points, but it's doing a good job modeling the trend exhibited by the original real world data. And that's what we can do for real life, is we're trying to determine a mathematical model that does a good job. All right, so we've got our quadratic regression, we've got our equation, and now let's use it to do some things. Let's use our model to predict the number of applications in the year 2015. So let's go back to our years since. Our years since 1990, 2015 would be from 1990 to 2000 would be 10, to 2010 would be 20, to 2015 would be 25, is that right, 25? Right now my window is only going to 20, so I better make my window 30. Right, I better make my X max 30. X max 360. So I went and changed my window to 30 so I was a little bit more past so that my 25 is going to fit on my graph. We can predict the number of applications in the year 2015 now that I have an equation by doing trace, right? I can do trace, but I need to make sure that I'm tracing on my equation, not on the scatter plot. So I'm going to do trace, and what am I going to enter? What was X when in the year 2015? What value is X? 25, and so I'm going to go ahead and do 25, but I need to go on the blue. Right now it's on the plot. So I need a down arrow to tell the calculator, use the equation, the y equals equation. Don't use the scatter plot. Use the y equals equation and enter the x value, 25. Enter. And the cursor will jump on the graph and pair 25 with the y coordinate, 481.6, and that's thousands. I just measured in thousands. So I need 3 more zeros. So it looks like 481,612 applications. That's pretty sweet. And lastly, in what year does the model anticipate the number of applications to surpass 600,000? Got to go back to my window again, you guys. Got to go back to my window. Right now, my Y max was 500, so that would be up to 500,000, and I need more than that. So I'm going to go ahead and change my window now to 40 X max, 360, and my Y max I'm going to put to 800. In doing this, I'm trying to make a better picture so that I can get to my predicted value of 600,000 applications. Let's see if that does a good job. All right, so I want to know when my blue regression equation predicts 600,000 applications. Is 600,000 applications, is that an X value or a Y value? 600,000, is that an X value or a Y value? That's a Y value. And so if I went ahead and set my equation y equal to that, then I could determine when it happens. So I'm going to go ahead and do a second y equals equation. I'm going to put in 600. Remember, I don't want this one. I'm going to put in 600. Remember, it's measured in thousands. So by putting 600 in the y equals menu, that's 600,000 applications. I'm now going to look at the graph and do a second calculate intersect. Again, this is my second trace calculate menu. I want to know when my blue model predicts the red 600,000 application level is reached. Everybody do it. Second trace is calculate. I want the fifth option for intersect. First curve, we have to go to the blue one. Yes. Second curve, we have to go to the red one. Yes. And guess, I can use my right or left arrow keys to get closer where I think it happens. It looks like this is only happening once on this picture, so I'm safe to press enter. And voila, the cursor jumps on the graph at the intersection point and predicts that the number of applications Y will be 600,000 at a time t of 30.4. Is that right? Is it saying 30? Yes? 30.4? So what would we say? Well, 30.4 years after 1990. So when's that? That would be 1990, right? 2000, 2010, 2020.4. So 2020? Is that what you guys are getting? 2020? That's 2020? Oh, yeah. So in the year 2020. So you can just sign the green book right there, and then NEC is fine, and you're just in time for our quiz. What questions do you guys have on number 3? Clearly, our graphing calculator is very powerful, right, in what it allows us to do using graphing calculator technology and the stat menu. However, I want to make sure that you guys have plenty of time to do your very best. So at this time, I ask that you take your faceplate and put it on your calculator. So the first part's on calculator. Everybody put the faceplate to close up their calculator. I'm going to stop the recording.